You're on.
Thank you so much. Thank you.
After some struggling with the laptop and the laptop switchover, unlike Peter Orban's talk, we at least have a full screen. Today's speaker is Lunagomez, who's currently based at UCL, who came to the UK first from Duke and then via Harvard. Simone has a broad range of interest, ranging all the way from putting graphical models to networks. And today he's speaking about sampling and social networks. Thanks.
Thanks, Sophia. Thanks so much for having me today. Thanks for coming to the seminar. So, since we are a small crowd, just please free to interrupt me anytime you have questions. So this is a project I developed with my previous mentor, Edoardo Airoldi at Harvard. So the motivation for thinking about this problem was that more and more often what happens is that we have social network data, we carry our inferences, but most of the time we condition on the data we have, and we don't take into account the uncertainty associated to the data collection process. So the first question is like, okay, does that matter in certain specific problems in social networks? So we're gonna see how that is addressed from a likelihood and Bayesian perspective. Okay, so I'll give you first. I'll present the applied problem that motivated this research. Tell you a bit about previous efforts on sampling of social networks. Then I'll tell you about the general idea, because what we're trying to do is not to propose a single model, but rather propose a framework or giving general ideas of how to propose different the underlying principles for, that can help us to propose different models for this type of problems. Then we'll discuss, we'll present a particular case for this type of models, how to perform Bayesian computation, simulation studies, and data analysis. Okay, so the problem that motivated this research was the following. So think of a population, and think of this population as capital N individuals. And these individuals are exposed by disease, for example, AIDS. So a relevant problem in epidemiology is to estimate the prevalence of the disease in a high-risk subpopulation. And this high-risk subpopulation can be, for example, men that have sex with men, people that use intravenous drugs, for example. So it's a highly stigmatized behavior. And these behaviors can be associated with a social network. For example, people that use intravenous drugs, the risk of transmitting the disease is associated with the fact that people use the drug and then they share needles with them. So that entails a social network. Men that have sex with men, well, the fact that people have sexual relations with one another, that also implies a social network. Okay. So what has happened is that people in epidemiology and social science have devised procedures for estimating quantities at population level, and then they realized that you can have better procedures by taking into account, better in terms of frequentist properties, by taking into account the social network structure. Okay. So some previous efforts for this type of problem will be the snowball sample, which was proposed by Goodman. But you can think of it this way. You can take a series of individuals, like starting points, also called as seeds, of this population. You take the measurement you're interested in, for example, they check the test for these starting points, and then you look at all the neighbors they have in the social network. And then you take the measurement of interest for all the neighbors, and you go to the neighbors of the neighbors and so on, and it propagates until you obtain a pre-specified sample size. Okay? So later this was refined by Heckathorn, and this refinement is called respondent-driven sampling, or RDS, and I'll tell you later with more detail what this is about, but the idea is instead of looking at all the neighbors, at least you take a subset of the neighbors, of another that already has been recruited, and you pick these neighbors according to the probability distribution. Okay. So later, RDS was coupled with an estimation procedure called the Horowitz-Thompson estimator. So now we have the sampling procedure, and then the next idea was like, okay, which estimator will better take advantage of this sampling procedure? That's what Horowitz-Thompson does. And the underlying idea here is that, okay, you're gonna take the measurement you care about. Let's think again of the result of a HIV test, 0 or 1, and you're gonna weight that, each of these measurements by the probability of getting that observation, okay? And there have been different approaches for doing that. One of them say, okay, maybe the probability of observing a given individual is a function of the degree, and you can think that it's a very simple function, like the inverse of the degree or something. But then you can, there have been further efforts for refining those, how to estimate those inclusion probabilities, the probability of sampling an individual. And there have, some of those efforts are the one by Guile in 2011 and the one by Crawford. Yes.
Are you assuming the network actually is a known?
No, the network is not known.
Oh.
The network is not known. So you're going to have partial information about the network. Okay? So, you will discover features of the network as you recollect your sampling. So I'll give you a concrete example later. So, okay, so this problem clearly has several components because it's going to be an underlying social network. We're not gonna have full knowledge of this network, and there's going to be the part of the network that you observe. But a part of the network that we're going to have measurements at the level of the nodes. So we're going to have different layers of uncertainty. So what we want to do is, okay, let's formulate an approach that is modular in the sense that we're going to look at the different sources of uncertainty, identify distributions that play those roles and how those distributions are related, and then see, okay, now that we see how the sources of uncertainty relate to one another, then we can think of how to specify each of these distributions or factors. Okay, so what are we trying to do? We're trying to propose methodology that is model-based, so we want to express our inference in terms of a likelihood, and we're going to propose a Bayesian approach, so it's going to be also priors. We want to take into account main sources of uncertainty, and one of these is going to be the uncertainty due to the sampling. And we want this approach to be modular in the sense that, okay, we're going to have different distributions modeling different aspects of the problem, but we would like to question these different distributions or assumptions separately and try to make our computation also as modular as possible. Okay, so the first step is to specify our likelihood, and a question that comes from this problem is like, okay, does the uncertainty due to the sampling mechanism, should that play a role in the likelihood? And that's the notion of ignorability. That's how we formalize this idea. So think of these four panels, these four social networks, and in these four panels, the same nodes, the same set of nodes is highlighted in black. Okay, so now, what's highlighted in black, we're going to regard as the part of the network that you observe, the nodes that you observe, and what's light gray is what we don't observe. Okay, so if we think of a procedure where we have a starting point, and then we start sampling according to this probability distribution some of the neighbors, and then we propagate like that. What's going to happen is, if we compare panel B and C, what we observe is, okay, we sample the same individuals, so we have the same individual included in the sample. We have the same underlying social network, so this is the light gray, but the way the sample propagate is different from B and C. So for example, we may have different starting points, or when we have the realization that was what depended from uncertainty led us to different subgraphs. So then when we compute the probability of getting that specific sample here and here, we're going to get different numbers. Okay? Now, if you compare C and D, what happens is that you observe the same individuals again. We have the same observed subgraph, but the underlying network is different, the light gray. So again, if we go through the exercise of computing the uncertainty of getting this sample compared to getting this sample, we get different numbers. Okay? So, so is this relevant or not? To what extent is it relevant? And that's where the notion of ignorability helps us to formalize this problem. So let W denote the full data, and this data has a certain distribution with parameter tau. So let Wi sub I denote the observed data. So W sub I will gonna be the black portion of the network before, and W can be the full network, for instance. So a sample mechanism, this is the probability distribution or process that generates the dark portion of the network. It's ignorable if the probability of that sampling mechanism, given the full data, instead, you can think the full network, can be expressed only as the conditional with respect to the part of the network that we observe or data that we have. Okay? And we also have that these parameters here of the sampling mechanism and these, and we're assuming that these two are distinct. So if this condition holds and these parameters are distinct, then we say that the sampling mechanism is ignorable. And what that means is that when we model the likelihood, when we write on our likelihood, we can forget about the factor involving the sampling mechanism. We don't need to model the uncertainty of the sample. So what matters is who is in the sample, not how the sample was collected. Maybe a bit more, elaborate a bit more on that. So in a sense, you have W, the full data set, and the sample mechanism is going to be random given W, and it's going to partition your data set in what you observe and what you don't observe. And we're going to follow the notation established by Rubin and write the joint distribution of these two this way. So first we observe the full data, and then we're going to partition it using the sampling mechanism. Okay? Okay, so the sampling mechanism we're going to be interested in is RDS, respondent-driven sampling, and the way RDS works is the following. So we're going to take a set of individuals, in this case it's going to be one, and we're going to take the measurement of interest in that individual, in this case the HIV test. So after we do that, we record the degree of this individual. We ask the individual what its degree is, and then based on its degree, we're going to sample a subset of its neighbors, and it's also always going to be the same number. We're going to call it, this number is going to be M, or number of referrals. So in this case, this individual has 5 neighbors, and we sample 3 out of 5. And then what we do is we iterate this procedure for the individuals that we recently recruited. So we're going to try to recruit at most M of these, M of their neighbors at each iteration. And there is only one constraint. We are not able to recruit an individual that has already been included in the sample. Okay? So what the subgraph that you observe, the one in red, is going to be either a tree or a forest. There's going to be no loops, no cycles. But observe that in order to do this, every time I recruit an individual, I have to ask the question, how many of your neighbors have not been included in the sample? Like, implicitly, that question has to be asked in order to compute these probabilities, to compute the probability of getting a sample. Okay, so then this procedure is done until, this mechanism is done until we attain a specific, pre-specified sample size. So then the question is, okay, is a procedure like this, like RDS, ignorable or not? Okay, first to answer this question, first we introduce some notation. Let G denote the social network, Y the vector of responses, the vector of 0 1s for the full network saying, okay, the HIV test for this person is going to be positive, negative, and so on. And I is going to be the sampling mechanism, okay? So here the sampling mechanism is going to determine, for starters, how the network is partitioned into the part of the network to observe and the part of the network to observe. I'm going to use the notation here a little bit. So here, GI is not going to only be a subgraph. It's not going to be only the 3 or 4 as observed at RDS, but it's also going to include the information about the degrees. Okay, we know the degrees of the nodes we sample. Let's assume we know them and they are not noisy. I'm going to talk about that constraint later. So then if we want to answer the question, is RDS ignorable, then if you write the distribution of RDS given the full network, it's going to look something like this. And what's important here is that these distribution involve these quantities. We call them the adjusted degrees. But what's important about them is what they encode, what they represent, is the answers of these questions. Like, if I recruit this node, how many of their neighbors have already been included in the sample, have been sampled already? And what's important about those quantities is that if what I have, if the data that I have is given by this observed tree of forest and the reported degrees, just the plain degrees, then I cannot recover these numbers from that data. So that means I cannot write this distribution as PI given GI. I cannot express it as a conditional only on the data that I observe. Then RDS is not going to be ignored. Okay. So that means that I need to consider the uncertainty of the sampling mechanism in my lab. Okay. So what are we trying to do? Okay. So at this point, what we're trying to do is to identify the key assumptions needed to construct a model for the main sources of uncertainty, the underlying network, the vector of responses, and the sampling mechanism. We want our models to be parsimonious. They're going to be complex. We don't want to be more complex than needed. And we want them to be amenable for Bayesian inference or computation. Okay? So what we want to propose is a modular approach. So there are going to be different parts of this model, and I should be able to specify those parts differently, but not only in theory, not only as how to say, specifying as an equation, but when I perform the inference, I would like to have general principles about how to do the computation, regardless of how I specify those parts. Okay. So given that, I'm going to introduce some more notation. So remember that the sampling mechanism divided the network in the part that I observe and the part I don't observe, G sub I and G sub E. Well, the same happens with the vector of responses, the vector of results of the HIV test. There's going to be the subvector for the nodes that I observe and the subvector for the nodes that are not included in the sample. Okay. We're going to ask, okay, there's going to be a social network involved. Think, for example, of the case of people that use intravenous drug and share needles. So how does this network enter the model? It enters in two ways. The first one, as we have elaborated before, well, the network constrains how the sample is propagated. It drives how the sample is propagated. Secondly, and this, we think is a very nice innovation in our methodology, is that, because we take this into account, is that the graph imposes a dependency structure in the responses. Think of the following. If you're in a social network and all of your neighbors have resulted positive in the HIV test, that affects your risk of being positive differently if all your neighbors were negative in the HIV test, regardless if you have the same number of neighbors in both cases. Okay, so it matters not only, it's not only a question of graph topology, it's also about the behavior of your neighbors. Okay? Okay, since we're interested in the case where the sampling mechanism is not ignorable, we have to model the distribution of the sampling mechanism explicitly, and we'll be forced to model the missing data. So ignorability implies that the probability of observing the sample depends on things we did not see. So one implication of that is we have to model or impute that part of the data we did not see. So this is the take-home message of the talk. This is what we're proposing. So we want to model all the main sources of uncertainty with the following factorization. So here we're going to have the network, the vector of response, and the sampling mechanism. So this factor in orange is going to be a random graph model. So here we're going to model this represents the part of the underlying social network. So here we model the uncertainty of the part of the network we don't observe. We have this, the factor in cyan models the uncertainty for the sampling mechanism. And the factor in red is what models the dependence of the responses given the network. Okay, we're going to have two parameters here. This alpha parameter here, or set of parameters, the vector parameters alpha is what specifies determines the distribution of the random graph model, and gamma is what allows us to determine this distribution. Think of it this way. In this distribution that models dependence among the y's, the g tells us who's dependent of who, so like a series of conditional dependence statements, and gamma encodes the strength of the dependence. You can think of it that way. So the objective is to make inference about population quantity, in this case, for example, the prevalence of the disease, or the average number of, the proportion of individuals that will be positive in the test for the whole population. So that you can write in terms of these quantities in this way. You can think it of, okay, we're gonna take we take the parameters. Given the parameters, we can simulate a network. We simulate a vector of responses given that network, and we take the average of that vector of responses. And this is, we just look at expected value of that. So, so that's the model, and so on. So how do we perform Bayesian inference here? So this is what we propose. So Q is the value we want to perform inference on. So the posterior of this quantity, given the responses that you observe, the part of the network that you observe, and the sampling mechanism, can be written in this way. So first we obtain the posterior for the part of the network, for the parameters of the social network, okay, and for the missing data, for the missing part of the network, okay? We get the joint posterior for these two. Now, you can think about it this way. Let's say I get this data, I run an MCMC, I get an imputation, I get a value for alpha and an imputation for the part of the network to observe. I use this imputation of the part of the network that I observe, and then what I have? Well, I can use this to join with the network part of the network that I observe, and then I have a whole social network. Well, if I have this social network and the responses that I observe, then what I have is a problem that only involves the strength of the dependence, and I would say, and the missing responses. They are not here, but they're going to appear later. But then once I make the inference for the strength of the dependence, well, I can plug in the output of my MCNC for this quantity and for the random graph model, and then I can get the feature that I'm interested in. So that's the way the computation is carried out. Basically, I have a mixing distribution that encodes what I've learned about the social network structure given my data. I use this knowledge, I impute the part of the network I did not see, and then I perform the inference on the strength of the dependence. And that allows me to get posterior samples for the population quantity Q. Okay, each of those steps, the update for the mixing distribution and the update for the MCMC inside the integral, both of them are carried in a similar way, in principle. So basically, you have a parameter you're interested in, and you have missing data. So you can formulate both of these problems as Gibbs samplers. Okay. So the second one can be a bit more complicated, since if you for the models we're going to use, they're going to entail say intractable normalizing constants, and I'll come to that later. But in principle, this is they work the same way. Okay, so I'm going to give you an example of how a model like this will be specified. We start with something simple. We can think of the random graph model as an Erdos-Shreni, and we put a beta prior on the probability of inclusion. Okay. For the dependence of the responses given the network, we can formulate it as a Markov random field, and this is we can use a specification like this. And this was this example is discussed in a paper by Jesper Moller, and where these two quantities take this form. So basically what we have is that this parameter gamma 1 encodes the dependence of the immediate neighbors, okay, of the network. So how the response in a given node is influenced by its immediate neighbors. And we use the prior for gamma as suggested in the paper by Moller. For the distribution of the sampling mechanism, we use the one implied by RDS, and we saw the expression before. Okay, so to sample from these conditionals, the ones I presented before. So we have these four conditionals in our problem. This can be done. This can be sampled via if they cannot be sampled exactly, they can be sampled via Metropolis Hastings. And this one is a bit more delicate because it entails, for this model specification, it entails a model with intractable normalizing constant, but then we can use the methodology proposed by Moller for something the posterior in those cases. And there's a whole literature for that. So how does our method comply, for example, with false hackathon? So here, this is what we do. We take a variety of regimes given by the density of the network. So we take the density of the network and keep the dependence fixed and the other factors fixed. Or we fix the density and we let the dependence vary, or we play with the number of nodes that we sample on the network, or the number of seeds or starting points, and then keep everything constant. And what we observe is that in terms of quadratic laws for the point estimator, like there is basically no difference. I mean, it's not false hackathon does a good job, and it's hard for us to improve. Now, but that's what we were expecting. In fact, what we were expecting, what we were hoping when we developed this methodology is like, okay, what we're doing is we're incorporating different sources of uncertainty, and we're trying to model them the best way we can. So maybe the point estimates are going to be very similar, but when you look at the uncertainty associated to those estimates, they're going to be very different, right? Because we're using all the data we have in a coherent way. So what we observe is in the same set of regimes is that when we look at the length of the interval, here we're comparing confidence intervals. It's going to be on cyan, and these are confidence intervals implied by the bootstrap. These are on cyan, or credible intervals. Those are going to be on red. We get much shorter confidence intervals across the regimes, but the coverage probabilities, if we look at them as the frequentist properties, in all regimes we get values that are very close to the nominal value. So this is so that's the game here. Like we can get much tighter, much shorter intervals for the same quantities, but with the desired coverage. So this is assuming that the model is correct. We recently got results now like challenging that assumption and using misspecified versions of the model, and the results were similar. I mean, these statements are robust, which was very nice, very encouraging. Okay. So then we so now I'm going to show you a data analysis example. So we applied our method for an RDS study performed in Campinas, Brazil. And in this study, the objective was to estimate the prevalence of HIV among men that have sex with men. So this was a study that comprised 658 individuals, and these are the inclusion criteria. And so the epidemiologists implemented this study using RDS with 16 seats and 3 referrals. Okay. So these are the results we obtained from our method, and this is what will be obtained using both second-term and the implied bootstrap interval. So in our method, if you may have noticed this, that okay, we impute the part of the network that we observe, but then one tuning parameter you will have is how large you are allowing that imputation to be, up to how many nodes you're going to impute. So that's going to be a tuning parameter. So the way we make sure that that tuning parameter is not affecting our results is by running a sensitivity analysis. So these are two portions of that network of that table with the sensitivity analysis. So here we are saying, okay, we're going to allow to impute twice the number of nodes as the sample size we have, and here 3 times the nodes. Okay. So what we observe here is that okay, the posterior mean for the quantity we care about is slightly higher. So the values here are consistent. The quantities of the posterior are more or less are very similar, and we get a slightly higher values for our point estimate than the Volkswagen. But again, our posteriors tend to be a bit smaller. Now, the difference is not as dramatic as the simulation studies, but that could be attributed that there can be some model misspecification issues going on, and we need to study that further. So we have kept working on this this problem. So we're about to resubmit the revision for this revised version for this paper, and we also been working on 2 extensions of this methodology. One of these extensions is the following. Okay, so what we did in this project is, okay, we look at these random variables and random quantities, and we propose a joint distribution for them. But in order to do that, we took the sampling mechanism at the starting point, and then we built machinery around it. We start putting distributions after the fact, after we have this sampling mechanism. However, in statistics, we tend to we should do things the other way around. We should say, okay, I'm going to assume a model of this form. I'm going to have a family of sampling mechanisms that I can parameterize by eta. Let's call it eta. And then what I would like to do is to calibrate eta. So So the properties of my inference are optimized. Okay. So this is turning this problem of inference into a problem of experimental design. And the way we approach this is via decision theory or via Bayesian experimental design. So that's what we're doing. So it's, that's very exciting. The other extension is, and we're excited about this, it is the following. So what happens a lot for this type of data is that there is not always a clear distinction between the part of the data that you observe and the part of the data that you don't observe. The part of the network you observe and the part that you don't observe. Now, for example, in RDS, what you work with are not the real degrees. There's no guarantee of that. You work with the reported degrees. People tell you, okay, this person tells you, okay, I had this many sexual partners in the last couple of years. So now think of it this way. If they can have few sexual partners, they're gonna report them with a lot of accuracy. So, okay, 3, 5. But let's say they have way more. They're gonna start rounding, 15, 20. But if they have way more, the rounding is gonna become more severe. Okay, 100. There are some people in our data that are sex workers. So you have those numbers. So what you have is you don't have the exact degrees. You have noisy version of the degrees, and the way noise can happen, for example, in this case, is that the higher the underlying value is, the more severe is the rounding, the more severe is the noise. So, and this is known as heaping. So how do we deal not only with, and heaping is a particular case of a phenomenon called coarsening, which is also discussed and explored by Rubin. So the thing is, like, how do we extend our framework or this discussion? So we don't talk not only of non-ignorable sampling mechanism, but non-ignoring coarsening mechanisms. And this implies not only that the coarsening does not only affect the social network, but it can affect attributes on the nodes, or maybe attributes on the edges. So how does this extend? Okay, so some final remarks. Our method is able to perform Bayesian inference for a small population quantity Q, and we take into account some of the main sources of uncertainty. We made the case that this approach is modular in the sense that it has parts that you can clearly identify. These parts can clearly will play specific roles. This can be specified in different ways, and we try to be explicit on what the constraints in that specifications can be, but also we have general policies about or general procedures about how the computation can be carried out. So it's not there are things we can say in general, regardless of how those parts are specified. So in this work, we tackle the problem of non-ignorability for sampling these isolate networks in a principled manner. Okay, what do we want to do next, apart from the two extensions we've been working on? Well, one obvious extension is to incorporate covariates, and here this has to be guided by the data, because you could introduce covariates at the level of the distribution of the responses, but you could also think of covariates at the level of the sampling mechanism. Like, for example, there is one individual and we ask him to recruit 3 of the neighbors in the network. He may refer to individuals that are more similar to him according to certain attributes. So involve ideas with the reference distribution. And so far, okay, the way we perform this computation, well, they involve MCMC schemes that are pretty demanding. So how do we scale this up to networks that are more related to other domains of application, millions of nodes or tens of millions of nodes? So, that's what I have to say. Thank you so much.
Questions for Simon?
Yes.
So this total size of the network seems a very, so you have imputed up to 3 times of the sample size.
Yes.
Is it a bit optimistic, or is there some guidelines of how big I mean, if you are thinking of a prevalence, it also depends on the population.
Yes, no, basically how to say, we look at the, we ask, how to say, someone familiar with this literature, and familiar with this literature, and that if it was reasonable to use these numbers. So, okay, for that population in Campinas, Brazil, okay, this is not too bad. So we went up to 4 times, and 4 times the sample size, and the results were pretty consistent. So basically what it's telling you, like, from this simulation, what it's telling you is that if you augment even twice, 3 times, or 4 times, you get essentially the same answer. So there is no, for the simulation, there is no, in terms of the Q, for the simulation, there is no reason that you should go higher. But yeah, so there is that question. If you went like much higher, you observe something different. And the question is, and so the thing is, with the simulation we have, and from what this suggests, it doesn't seem to be the case. But how to say? But that's something we would like to explore. But that will mean that we will need to scale up these simulations for the tens of thousands, so which at this point will be like very, very slow. So it takes a whole afternoon to run a simulation like this. So that's it. So that's the thing. So yes, but I guess it's so what I would suggest is to start like increasing the sample size of your the size of your imputation, and then run a sensitivity analysis and see how much does it affect changing the maximum size of the network you're imputing in your answer. Okay, so that will be the first that will be the answer we have so far.
I have a second question about
Yes.
your heaping effect, which I
Yes.
think is quite interesting. Is most of that literature coming from observational social science, or is there also literature in the physical sciences? Because you would imagine that just making analog acquisitions, the accuracy would change depending on what part of the measurement space you were in, or has this mainly been developed within the social science context?
So I think the references to go here are the ones by Dan Heishtan and Don Rubin. So they have done a lot of work on it. If I remember correctly, most of their applications come from social science, but maybe there is work in the natural science. We'll have to check his work.
There's also like quantization effects, but these are not quite quantization, because your quantization will change its resolution as you get the higher value. So it's like a generalization.
I was wondering about, I mean, the question of scaling up computation kind of always comes up with these types of methods, but do you see any, I mean, easy to put down, but possibly hard to solve? I mean, do you see any ways to address scalability, like that might be specific to this or other network contexts?
So that's a very good question. So that's we haven't put that much effort on thinking of the scalability. That's something which definitely in the agenda. So here is that the connection with frequentist methods and other ways of thinking is very useful, because I would say, in a sense, what we're trying to do here is say, okay, let's try to do everything as principled as possible. And then when I understand, when we understand that, when we have better understanding of this, then we can say, okay, maybe we can start for other regimes, like higher network, maybe we can start resorting to asymptotics or some other type of tools. So I guess I guess that would be one approach to see how asymptotics can kick in the picture here. The other thing that can happen, the other possibility I see, and I think it's promising, is like, can we think of models, especially for the network, can we think of models that have that are flexible, but have nice sufficient statistics? Okay,
Yeah.
so if we have promising models that have sufficient statistics, or statistics that are close to sufficient, then the problem scalability is not a problem, because you do that step as a pre-processing, and then you run your CMC as well. So how to say? I've been thinking more about this later approach, but how to say? But I think the discussion should be also open from the side of asymptotics.
Okay. Any more questions? Thanks, Monica.